Let's first think about making a regression prediction. We've picked an x value. We want to know what's an average y value for that x value. The height of the regression line is exactly that for the sample. But what about for the population? Well, since we've sampled, there's some variability in the height of the regression line at any given point. And can we somehow characterize that variability? Well, we can by using a confidence interval around the height of the regression line at a particular point. So we're performing regression prediction. If the data comes from the regression model, then the regression line is close to the true line, but not exactly the true line. So given a new value for x, we want to predict an average value for y by finding the point on the regression line at that x. But we want to account for the fact that if we had drawn a different sample from the same population, the same regression model, then we would have gotten a different regression line, and so it would have a slightly different height at that value x. We're going to use confidence intervals, but instead of them being around an estimate for a particular parameter, they'll be for an estimate of the height of the regression line at a particular value x. We'll do this by bootstrapping the scatter plot, the sample that we have available, getting a prediction for y using the regression line through the bootstrapped scatter plot, and repeat this 2 steps many times in order to look at the distribution of different y values that we get for different regression lines. We'll draw the empirical histogram of all those predictions. The middle 95% of those will be the confidence interval. That's an approximate 95% confidence interval for the predicted value of y, or restated, a confidence interval around the height of the true line at that point x. Onto the code. Here's one row per baby. We have the birth weight and gestational days. And we saw before that it appears there's a linear association between these 2 measurements of a baby. R is 0.4, and the root mean squared error is 16.7 ounces. Where a typical baby is something like 120 ounces. Heavy ones are up at 175, and light ones are closer to 60. Looking at the residual plot, it appears that this is a fairly linear association. I don't see a lot of structure in this plot, except for maybe in the very far extremes. But let's focus on the data in the middle. That seems to be an amorphous blob. So let's pick an x value. X equals 300 days. The slope and the intercept from this sample of babies gives me a predicted y value. And we'll draw that on the scatter diagram. Here's the regression line for days versus birth weight. And here is the height of the regression line at x equals 300. The predicted y is 129. The way we got that prediction is to compute a slope and intercept, and then find the height of the line at that particular value x. Now this is for the original data that were observed, but we could also perform the same process for a resample version of the same data. We started with 1,174 babies. Here we draw 1,174 babies. With replacement, we get a predicted y from that set of babies and draw a scatter diagram that looks just like this, but with a different set of dots. And let's do that 4 times so that we can see the variation. The scatter plot looks about the same. X is 300, we're holding fixed. That's the x we're interested in. And the y value that we get from performing regression is again pretty close to 129. Here's another scatter diagram from another resample. It really is different. Like you can see that these dots are not the same as these dots. And yet, the height of the regression line at x equals 300 is just about the same yet again. Here's another resample. Here's the height of the regression line. This time it looks like it's more like 132 or so, but pretty close to 129. And here it's right around the same area, right around 130. So, to carry out the process of computing a confidence interval, we don't just draw this scatter diagram 4 times, but instead generate it many, many times, 100 or 1,000 times, and look at the distribution of heights of the regression line at x equals 300. First, let's just draw 10 different regression lines. So these are 10 lines that we get by resampling from the actual babies observed and then drawing a regression line through the new sample, through the new scatter plot. We get almost the same line every time. In fact, where it really counts, where most of the babies are, all of these lines are about the same. Now way here out at the edges, where there are very few babies, the lines diverge because we don't have as much information about the association between gestational days and birth weight way out in this part. And the same goes for very high values. But within the center of the cloud, resampling doesn't give us wildly different regression lines each time. It just shows you how it might vary a little bit when you only have 1,174 babies to look at instead of all the babies that ever might have been born. Let's do the same process, but just zoom in on the part we care about. X equals 300. 10 different regression lines from 10 different resampled versions of the dataset, all cross 300, x equals 300, at a y value between 128 and 131. That's the kind of variability in y estimate or y prediction that we might expect if we had drawn a different sample from the original population. And so, we can perform the bootstrap to compute a confidence interval using this kind of reasoning. Many times, we take a resample, 1,174 babies drawn with replacement from the original babies. We compute the slope and intercept of the regression line through this new resample. It might be slightly different from the regression line through the original sample. We form a prediction where we're interested in new x equals 300 and the slope and the intercept from the resampled data. And we keep that prediction around. Using those predictions, now we have a bunch of them, we find the left and right bounds of an interval with width 95%. And then we display the results. Here, we're making 5,000 repetitions of the process. And we're focusing on x equals 300. And we get a 95% confidence interval that our prediction should be somewhere between 127.3 ounces and 131.3 ounces, or a width of about 4 ounces. And that width is because if you draw a histogram of the different predictions from resampling, it's normally distributed, and most of the values fall in this range described by the confidence interval. Now, let's go back to this picture. When you resample, you get different lines, but those lines are all very similar in the center of the data, and they diverge out at the extremes of the data. And that affects the width of the confidence intervals that you get. So if you ask for a confidence interval right around x equals, say, 280, you're going to get a very narrow one because all the lines are the same there. If you ask for a confidence interval out at x equals 320, you're going to get a wider confidence interval. And we can use computation to show that this is the case. So let's look out at 330. That's far to the right of the bulk of the values in the scatter diagram. And here we are. A confidence interval around the estimate for the height is 139 to 148, which has a width of 9 ounces instead of 4 ounces because we're farther away from the center of the x distribution. But if we want to figure out the height of the regression line in an area where we have lots of data, then we should get an even narrower width. And that's exactly the case. For gestational days of 280, we get a confidence interval from 118.9 to 120.8, which has a width of less than 2 ounces. So at 95% confidence, we're picking a pretty narrow range of reasonable y estimates. So the width of the interval when you're doing prediction confidence interval estimation is going to depend on where you are on the line. in terms of the x position. It's also going to depend on the distribution of the data, how spread out it is, and how many data points you get to observe. The way in which you account for all this information is to perform the bootstrap, and that gives you a confidence interval.